Script. Hey everyone, welcome. Today we're tackling a Leetcode problem called Lowest Common Ancestor of Deepest Leaves. Sounds a bit fancy, right? But don't worry, we'll break it down step by step. It's about finding a specific node in a binary tree. Let's dive in. Script. Okay, so here's the official problem description. We're given the root of a binary tree. Our mission is to find the lowest common ancestor of all the deepest leaves in that tree. Let's unpack those terms. A is just a node with no children. The other node is how far it is from the root. The root itself is at depth 0. The deepest leaves are simply the leaf nodes that have the greatest depth in the entire tree. And the lowest common ancestor, or LCA, of a set of nodes is the lowest node in the tree that has all those nodes as descendants. Basically, where their paths back up to the root meet. So we find all the leaves at the maximum depth, and then find their common meeting point that's furthest down the tree. Script. Let's look at the first example. We have this tree. Notice nodes 7 and 4. If you count the levels down from the root, which is 3, you'll find 7 and 4 are at depth 3. Are there any leaves deeper than that? Nope. Nodes 6, 0, and 8 are also leaves, but they are only at depth 2. So 7 and 4 are our deepest leaves. Now where do their paths back up to the root meet? Node 7's parent is 2, and node 4's parent is 2, so node 2 is their lowest common ancestor. That's our answer. Script. Here are a couple more quick examples. If the tree just has one node, like Halashir, well, that single node is the root. It's the only leaf. It's the deepest leaf, at depth 0, and the LCA of itself is itself. So we return node 1. In the third example, the deepest leaf is node 2, at depth 2. Since it's the only deepest leaf, its LCA is just itself again. So we return node 2. Make sense? It covers these simpler cases too. Script. So how might we approach this? A first thought might be, well, let's find all the leaf nodes first. We could do a traversal, maybe depth first search, DFS, and keep track of the depth of each leaf we find. Then, we figure out what the maximum depth actually is. After that, we gather up all the leaves that are exactly at that maximum depth. Finally, we'd need another algorithm to find the lowest common ancestor of just that group of deepest leaves. This sounds like it could work, but maybe involves multiple passes or complex bookkeeping. Could we do better? Script. Let's think recursively. What if each node could ask its children about the deepest leaves below them? Imagine a function that, when called on a node, returns two pieces of information. First, the depth of the deepest leaf it found in its entire subtree, and second, the actual node that is the LCA of those deepest leaves within that subtree. If we could design a function like that, the answer for the whole tree would just be the LCA node, returned by calling this function on the root. Script. Okay, so how does a node use the results from its children? Let's say the left child returns its info, left underscore depth, left underscore LCA, and the right child returns its info, right underscore depth, right underscore LCA. The current node compares the depths. If the left side found deeper leaves, left underscore depth is greater, then all the deepest leaves must be down that left path. So the current node passes that result up, just remembering to add 1 to the depth because we've moved up a level. Same logic if the right side was deeper. But what if the depths are equal? This is the crucial part. If both children found leaves at the same maximum depth, it means the deepest leaves are spread across both subtrees. The meeting point, the LCA, must be the current node. So in this case, the node returns the shared depth, plus 1, and itself, as the LCA. Script. Every recursion needs a base case. What happens when we try to go beyond a leaf node, hitting a null spot? Well, a null node doesn't contain any leaves, let alone deep ones, so it should return something that signals this. A good way is to return a depth of 0, meaning no leaves found here, and none, or null, for the LCA node. This ensures that when a real leaf node gets this result from its null children, it correctly identifies itself as the deepest leaf, at depth 1 relative to its parent's call. Script. Alright, let's look at the Python code that implements this recursive idea. We define a main function LCA deepest leaves, and inside it, a helper function, often called DFS, or helper. This helper function is the recursive part that does the real work. Don't worry if it looks like a lot at once, we'll zoom in on the key parts next. The main function just starts the process by calling the helper on the root, and then returns the second value from the result, the LCA node itself. Script. First, Let's look at the start of the helper function. It takes a node as input. The very first thing it checks is the base case, if not node. If the node is null, or none in Python, it means we've gone past a leaf. As we discussed, it returns a pair, 0 for the depth, and none for the LCA node. Simple enough. Script. Next, if the node is not null, the function calls itself recursively on its left child and its right child. See how it calls helper, node.left, and helper, node.right. It stores the results. Remember, each call returns a pair, depth, LCA, into variables like left_depth, left_LCA, right_depth, and right_LCA. So, after these two lines, the current node has the answers from its left and right subtrees. Script. Now comes the core logic we talked about. It compares left_depth and right_depth. If the left depth is greater, it means the deepest leaves found so far are in the left subtree. So it returns the left_LCA, and the depth becomes left_depth plus 1, adding 1 for the current level. If the right depth is greater, it does the same, but using the right side's results. Right_depth plus 1, and right_LCA. And the final else case is when the depths are equal. This is where the current node becomes the LCA. So it returns left_depth plus 1, or right_depth plus 1, they're the same, and the node itself. Script. Finally, back in the main LCA deepest leaves function, we kick off the whole process by calling helper. Root. This call will eventually return the final pair, the maximum depth of the entire tree, and the overall LCA of the deepest leaves. Since the problem only asks for the LCA node, we unpack the result using underscore. LCA_node equals. The underscore is a common Python convention for ignoring a value we don't need, and then we simply return LCA_node. And that's it. Script. So how efficient is this recursive approach? Time-wise, it's pretty good. We have to visit every node in the tree exactly once to figure out the depths and LCAs. If there are nodes, the time complexity is proportional to n, which we write as big O of n or order n. What about memory, the space complexity? This depends on the depth of the recursion calls on the system's call stack. In a perfectly balanced tree, the height is roughly log n, so the space is order h or order log n. But if the tree is completely skewed, like a linked list, the recursion could go n levels deep, making the space complexity order n in the worst case. Script. Alright, let's recap the main points. We needed to find the lowest common ancestor, but specifically for the set of leaves that are furthest from the root. A neat way to solve this is using recursion. We designed a helper function that returns not just the potential LCA from a subtree, but also the maximum depth found in that subtree. By comparing the depths from the left and right children at each node, we could decide whether the true LCA lies deeper on one side, or if the current node itself is the LCA, because the deepest leaves are balanced beneath it. This gives us an efficient order n time solution. Script. Hope that breakdown made sense and helped clarify the problem and the recursive solution. If you found this useful, please hit that like button. Consider subscribing for more Leetcode explanations. And feel free to drop any questions or thoughts in the comments below. And hey, if you're feeling extra supportive, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll see you in the next video.